Hey everyone, today we'll have a brief introduction to Newton's second law of motion. I am using the dark mode. Let me know if you guys like it. If not, we can go back to the regular mode. Okay, Newton's second law of motion says a change in motion is proportional to the motive force impressed and takes place along the straight line in which that force is impressed. That sounds very complicated, but it could be summarized in one equation. And it says acceleration, and that's a vector, is equal to the sum of the forces divided by the mass. This symbol is the Greek letter sigma, capital sigma. All it means is adding forces, the sum of the forces, meaning if we have more than one force acting on an object, we have to account for all of them. Some textbooks show this law. For instance, OpenStax, they show it like this. Acceleration is equal to the net force divided by the mass. Please know that these two mean the same. The net force is the sum of the forces. Okay? I will use this version of the law, this representation, because of what we'll do with free body diagrams. Okay? So if I do a very simple algebra step, so let me copy this one. So let's say if I multiply times mass, both sides, and then I use my reflexive property, that means I'll write force to the left. I'll have the sum of the forces is equal to mass times the acceleration vector. And I think this is the way most of you have heard it before. Normally it is taught as F is equal to mass times acceleration, F equals ma. But this is the way we'll use it because we have an algebra-based college class, so we have to use this one. And if we think about the text, a change in motion, that represents the acceleration proportional to the motive force, and it takes place along the straight line in which that force is impressed. What that means is if there's a force, like for this case, okay, just for this case, there's a force to the right, meaning that the acceleration will be toward the right. Okay, that's all it means. The direction, if there's an acceleration, the direction of the net force will have that same direction. If there's an acceleration to the right, there's a net force to the right. Okay. So now let's think about the implications mathematically of what that means. Well, the first one is force and acceleration are directly proportional. Are directly proportional. See what that means. Okay? So that means, let's use the equation again. Force is equal to mass times acceleration. That means if the force increases, that means the acceleration will also increase. Conversely, if the force decreases, the acceleration decreases. If one goes up, the other one goes up as well. If one goes down, the other one goes down. Okay? Next, we'll have the second consequence of Newton's second law of motion mathematically, and that is force and mass are inversely proportional. Let's see what that means. So we have I'm going to write the second law now in this form because I think it shows a further implication of everything. So, you know what? No, let me start with the regular one. And then we'll go to the second one. So there you go. Force is equal to mass times acceleration. Okay. So if the mass goes up, the force has to go down. Okay. If the mass goes down, the force has to go up. So if one goes up, the other one goes down. If one goes down, the other one has to go up mathematically. Okay? And then from this one, we can say, well, because acceleration and force are proportional, we can apply the same thing. Okay? And say if mass goes up, then the acceleration will go down. If mass goes down, the acceleration has to go up. Okay, that's important to remember. All right, before we keep discussing Newton's second law of motion, we have to define what a system is, because it's going to sound redundant, but we're going to have to define a system. A system is simply an object or a collection of objects. And the reason why we have to define a system is so that we can define an external force. What is an external force? Well, it's simple. It's that thing, use your intuition. It's a force external to the system. In other words, a force acting from without or from outside the system. Okay? And the way I like to think about it is whenever I have a physical situation, I like to think, okay, what is getting pushed? What is getting pulled? In this case, the car is getting pushed by this person. This person is applying a force. So I will define my system to be the car. So this is the system, and the external force will be the force applied by the person. So this one here, that is my external force. Okay? System, what's getting pushed, what's getting pulled. How about a collection of objects? Well, in this case, if you think about it, if we try to define the system as just a wagon, then there's no force applied by the kid. So the kid, then we don't take it into account, but we have to because the kid is adding mass to the system. So for this setup, we would have to define the system to be the kid in the wagon. So that's our system. And the external force is the force of the adult, right? This lady pushing this kid. That's how you define a system. Okay, what about the net external force? Well, sometimes you have more than one force acting on an object or on the system. So the net external force should be, or we can define it as the vector sum. Vector sum. That means you're going to add all the vectors. Vector sum of all forces acting on the system. For the previous two examples, we only had one person, one force being applied. Here we have two forces. Well, there's more than the two forces, right? Because we have friction, but we're not going to worry about that. So as you can see, we couldn't just say, oh, this girl's pushing the kid. Now we will have two girls pushing the kid, so we would have to account for all the forces acting on the kid wagon system. Okay, that's what net external force means. Combining all the forces. Okay, so sometimes these type of diagrams can get very messy, right? This one has a lot of arrows and it's kind of hard to see. So for this unit, we'll draw many free body diagrams. And another way you'll find in textbooks is force diagrams. And the name, it is very explicit. So free body diagram is a diagram showing all vector forces acting on the system. The best way to learn free body diagrams is by practice. Okay, so let's do a few examples. The first one says, for each of the following situations, draw a free body diagram and show the net external force. Okay, a book rests on a table. Here's my book on a table. Very simple. The first thing I have to do is, I don't start right away with the free body diagram because we're learning, so I'm going to use my sketch. And I'm going to find the center of mass of the book, which is the center. For most objects, it'll be the center. And then now I have to think what forces are acting on the book. Well, I know that the weight of the book, because of the force of gravity, points down. And we said that we'll call that one the force of weight. So Fw. And then, well, we said that the book is not falling down, is on a table. The table applies a force. It is equal and opposite because there is no motion up or down. So the arrow has to have the same length. And that one we call normal force. And I'm going to use a curvy N, kind of weird like this. That's how the textbook shows it, so I'm going to stick with it. And that is the normal force. Okay, so for the free body diagram, what we'll do is we'll kind of erase the book and the table and just keep the center of mass and the forces. So the free body diagram looks like this. We have the center of mass of the book. Then I draw my arrows showing the vector forces. They're equal and opposite in length. And then I have my force of weight, the weight of the book, and the normal force. This represents the weight of the book, right, going down because of the direction of the force of gravity and acceleration of gravity, center of mass of the book, and the normal force applied by the table. I think it's good if we define what the normal force is, because you may think normal in the sense that it is ordinary, but that's not the case. Let's define normal force, okay? So normal force is a force applied by a surface, that is perpendicular to the surface. In this case, normal, it's a mathematical term for perpendicular. If you think about it, the surface is the table. So here we can clearly see that there's a 90-degree angle between the force applied by the table, which is the surface, and the surface itself, okay? In mathematics, normal means perpendicular. So a force applied by a surface perpendicular to the surface, okay? The surface could be the ground, it could be a table, a chair, whatever. If it's a surface and there's an object on it, there's a normal force perpendicular to the surface. Okay, so now let's try another one. This one says, a student pushes a box across a classroom. So I have my little sketch. I have to define a system. For this one was easy, right? Because it was just an object there. For this one, well, what's getting pushed? The box. So that's going to be the system. I find its center of mass. I'm going to assume it's here. And then the external force will be the force applied by the student. So now let's define the forces. So I'm going to have, we're going to use green now for the forces. The weight of the box following the direction of gravity. So that's the weight of the box, force of weight. And then notice that there's a motion to the right, okay? Now, let's assume the acceleration is to the right. Okay. That means up and down, there's no acceleration, there's nothing happening. Don't forget that we like to treat x and y as independent. Motion along the x and y is independent, which means the normal force applied by the ground is equal and opposite to the weight. So here's the normal force. Then there's the push by the student, the applied force. So I'm just going to call it F. That's the force by the student. And because it's the ground, there's friction, okay? Frictional force. And friction is going to point to the left. Notice how the length of the friction vector is less than the length, or the length is smaller than the force applied by the student. That way it can justify that there's an acceleration to the right. This force is winning, right, is beating the frictional force, and let's call that one force of friction, okay? Because if they had the same length, then I couldn't say there's an acceleration, because then they would cancel each other out and there would be no net external force, okay? So now let's define frictional force briefly. We will have a further discussion of frictional force later. And that is a force applied by a surface that is tangent to the surface. A way to think about the tangent, what it means, is that friction is going to be parallel to the surface. The reason we don't use the word parallel is because friction is going to change direction based on motion, okay? So I'm going to add that friction opposes relative motion. Relative motion that is parallel or anti-parallel to the motion. What that means is if this student decided to start pushing to the left, then friction would switch and now point to the right, okay? It opposes relative motion. That's all you need to know for now, okay? That's all you need to know for now. And something I did to keep the length of the video short is I did not include the net external force. I did not show it. We'll do that in a separate video. Okay, let's do one more. This one I got from the homework, and it says draw a free body diagram based on the image below. So for this one, no net external force. It requires more skills with trigonometry. That's a later topic. It says a book is at rest on an incline as shown below. A hand is in contact with the top of the book, produces a constant force F hand vertically downward. Let's do a free body. Let's draw a free body diagram. I want you to pause the video, give it a try, and then we'll check. All right. So we have the book. Notice that the surface in this case is an incline. However, the force of weight, because it's based on the force of gravity, always points downward, straight down, okay? If the ramp, the incline would disappear for some reason, the book will fall like this, not at an angle, just down. That means the force of weight, the weight of the book, is down like this. Okay? And then, well, the force of the hand is pushing down, so there it is. If the hand were to be released, then the book would slide down the incline. Well, that means if it's sliding down the incline, friction is going to be up the incline. So friction is going to point like that. I'm not drawing the arrows to scale. This is just to show the direction. So force of friction. And now let's say if the hand decided to push the book up the incline, now friction would switch and point down the incline. Okay, it opposes motion. Also, there is a surface, so that means we have to have a normal force because there is a surface, and normal means perpendicular, so it has to be perpendicular to the surface, to the ramp. So that means my normal force vector would go like that. Okay? The reason why is if you continue this line, here's my 90-degree angle. Okay? Let me try a different color so it's more obvious. So I continue the direction of the normal force, and here's my 90-degree angle. There you go. So now how do we draw the free body diagram? Well, as we said, we draw the center of mass. We'll draw an incline to have the reference. Okay? I'm just going to copy the incline to have the reference, and then I'll erase it. There you go. So then we have the weight of the object. And then we have the force applied by the hand. I'm doing separate arrows because your homework has it like that. I wouldn't draw it like this, but it's fine. Doesn't really matter. I would just combine the two arrows and make a bigger vector and say this is the weight plus the force of the hand, but this is fine. This is force of hand. This is an H. Even doesn't look like it. And then we said friction is up the incline. So force of friction, and then the normal force perpendicular to the surface. These vectors are not to scale, okay? These are not to scale, but then we'll get rid of the incline. This is how my free body diagram would look. And that's it for now.